A rocket engine nozzle with cooling channels hidden inside its walls can now be manufactured as a single piece. This is significant because mechanical engineering is no longer limited only by what we can design. It's increasingly limited by what we can manufacture. Mechanical engineering can look like a solved discipline. Gears, bearings, shafts, springs, engines, pumps, and structures have been studied for generations. But the machines are changing because the tools available to mechanical engineers are changing. New materials let components survive conditions they couldn't previously tolerate. Computational optimization can generate geometries a human designer would struggle to produce manually. And new manufacturing processes are turning some of those geometries from mathematical models into physical parts. For this two-part series, we are not just looking for technologies that sound futuristic. An innovation has to solve a real engineering problem, enable a design that was previously impractical, or fundamentally change how a component gets manufactured. And it has to be recent enough that its practical development is happening now, in the 2020s and beyond. This is part 1, covering the first 5. All 5 are connected by one idea: the removal of constraints. First, large-scale metal additive manufacturing. Using metal deposition to build large structural components directly from a digital model, rather than as many smaller pieces assembled afterward. The problem: large complex metal components are expensive and difficult to make. Traditionally, a large part might require casting, forging, machining, welding, and assembly. And every step adds tooling, waste, tolerance stack-up, and potential failure points. Additive manufacturing changes the sequence. Instead of starting with a block and removing most of it, the machine deposits material approximately where it's needed. NASA's Rapid Analysis and Manufacturing Propulsion Technology program has demonstrated this at scale for rocket engine hardware. One printed nozzle was about 40 inches in diameter and 38 inches tall, with cooling channels integrated directly into the structure. NASA has also built a one-piece thrust chamber assembly this way, with a mass reduction of about 40% compared to the conventional approach. The advantage isn't just that a printer makes the same part faster. The process changes the part's architecture. Cooling channels become integrated, multiple components become one, and some assembly steps disappear entirely. Conventional manufacturing imposes geometric constraints. A cutting tool needs access, a drill needs a path, a mold needs to release the part. Additive manufacturing removes some of those restrictions, though not all. Deposition accuracy, residual stress, surface finish, and material qualification remain real problems. But the scale is changing what engineers can reasonably consider manufacturable. Which raises the next question: who decides what that geometry should look like? Second, topology optimization, a computational method that determines where material is structurally necessary within a design space, based on loads, constraints, and objectives like minimizing mass or maximizing stiffness. Traditionally, an engineer starts with a manufacturable shape and removes material from it. A hole here, a larger fillet, a thinner wall, constrained by experience and by what the manufacturing method allows. Topology optimization reverses that logic. Give the algorithm the design space, loads, and constraints, and it searches for material distribution that satisfies them. The result can look almost biological, but it's just following load paths. The Oak Ridge National Laboratory has used this to reduce component mass while maintaining mechanical performance. In one geothermal drilling application, a topology-optimized rotor cut its polar moment of inertia by nearly 50%, while keeping the required rotational stiffness and torque transmission. A geometry that couldn't be machined conventionally, so it was 3D printed instead. That combination is the real innovation. A shape a milling machine can't reach is useless. A shape additive manufacturing can produce becomes physically meaningful. Better manufacturing enables more design freedom, and more design freedom makes optimization more valuable. That's two constraints gone so far: the shape of the toolpath and the shape of the design process itself. Topology optimization still assumes one thing though, that the component is a conventional solid. The next innovation removes that assumption too. Third, lattice structures and mechanical metamaterials. Structures whose behavior comes not just from what they are made of, but from the geometry of their internal architecture. A controlled network of struts, surfaces, or repeating cells instead of a solid mass. A solid component often carries material that's doing very little mechanical work, but simply removing material creates weak points. A lattice lets you look from a different angle. Not how much can we remove, but what should the material be doing? By tuning the geometry of millimeter scale cells, engineers can control stiffness, strength, energy absorption, and even Poisson's ratio. Some architectures, like auxetic structures, get wider when stretched, rather than narrower. Additive manufacturing matters here because conventional machining can't create thousands of interconnected internal features. Modern metal additive manufacturing can produce a wide range of lattice unit cell geometries, and there's now enough experimental data to compare how different topologies affect modulus, yield strength, buckling, and energy absorption. These structures aren't magic though. Their properties depend heavily on relative density, defects, surface quality, and loading direction. And the National Institute of Standards and Technology specifically flags lattice and topology-optimized geometries as a new challenge for dimensional inspection and qualification. The real shift is that internal architecture becomes a deliberate design variable. And once you can control the inside of a component, you don't have to use that space only to carry loads. You can use it to move fluid. Fourth, additively manufactured thermal management structures. Heat exchangers and cooling channels with internal geometry optimized specifically for heat transfer. Getting heat into or out of a component efficiently often needs more surface area and better flow than conventional manufacturing can provide. A drill can't turn a sharp internal corner. A mill can't reach every cavity. A mold has to open. Additive processes can create internal passages that are difficult or impossible to make conventionally. NASA has produced rocket engine components this way. An earlier copper combustion chamber liner contained more than 200 cooling channels circulating cryogenic hydrogen to keep the chamber wall from melting. It's not limited to rocket engines. Research funded by the Department of Energy, including a Boeing project, has explored additively manufactured heat exchangers with complex 3D channels conventional manufacturing couldn't produce. And the Oak Ridge National Laboratory has built heat exchanger architectures via laser powder bed fusion specifically to enable unconventional flow paths. This is where the previous innovations converge. Topology optimization decides where material is needed. Lattices control internal geometry. Additive manufacturing builds it, and thermal engineering uses the resulting complexity to control flow and heat transfer. The result isn't just lighter or stronger. It performs a different function because of its internal geometry. So far, every constraint we've removed has been about geometry in metal. But geometry isn't the only lever. The material itself can be engineered, not just shaped. Fifth, continuous fiber additive manufacturing. Printing continuous carbon or glass fiber through a structure so reinforcement follows specific load paths, rather than printing polymer alone. This solves one of the biggest weaknesses of polymer additive manufacturing. Printed material can be light and geometrically flexible, but not strong enough structurally. Conventional composites solve this by embedding fiber in a matrix, but traditional composite manufacturing needs tooling, molds, and careful layups. Continuous fiber additive manufacturing combines both approaches. Reinforcement can go only where loads demand it, along a beam, around a joint, along a path an optimization algorithm generated. The Oak Ridge National Laboratory has developed hybrid processes combining additive manufacturing with compression molding, where continuous carbon fiber is selectively placed to create built-in stiffeners. In one such configuration, testing showed a 57% increase in flexural strength and a 49% increase in flexural modulus. The deeper idea? A composite doesn't have to be mechanically uniform. Carbon fiber is strong along its length, so engineers want it pointing in useful directions. And additive manufacturing can deposit that reinforcement directly along the component's geometry, converging with topology optimization, so one system decides where structure is needed and another decides where reinforcement goes. This is still an active research field. Fiber alignment, voids, bonding, and process control remain real challenges. But the shift is visible. Instead of manufacturing a material first and shaping it after, engineers are increasingly building the material architecture and the component geometry together. 5 innovations, 1 constraint each: tool access, design intuition, solid material, flat geometry, uniform composites. Individually, any one of them is a useful manufacturing trick. Together, they start to look like a different design process entirely. One where the algorithm decides the structure. The printer builds exactly that structure, and the material itself is engineered rather than just shaped. That convergence is more interesting than any single number in this video, and we've only covered half of it. Part 2 goes past geometry, into the innovations changing what the material is doing at the microstructural level, and the ones changing how engineers verify a part actually works before it's ever load tested. If you value engineering content like this, consider subscribing to Engineering Manual.